In section 2, we're going to talk about conditional probability and independence. So first we're going to talk about independence, and it has a different definition than it relates to probability. So independence is the probability one event occurs does not affect the probability of the other event occurring. So we want to take a look at a couple examples and determine which of them are independent. So when I draw a queen from a deck, replace it, then draw another queen. So if I'm comparing those, drawing a queen and then drawing another queen after I replace a card, that is independent. So that one would be yes. Getting an A in zoology and getting an A in biology. Getting an A in zoology does not impact getting an A in biology, so those are also independent. Being a Republican and liking football, those are not related, so those are independent. But our last example, drawing a king from a deck, the drawing an ace without replacing it, those are not independent, because if I draw a king and I don't replace the card, the likelihood of drawing an ace changes based on that. So the last one is not an example of independent events. So the reason that independence is so important is because there are different rules when we want to do probability problems that involve and, which is when both events occur. And this is similar to section 1 when we learned how to do or with two events using the additional rule, that were disjoint or not. So the multiplication rule for independent events says that if A and B are independent events, then the probability that A and B both occur is given by the probability of A and B equals the probability of A times the probability of B. So that upside down U represents the word and. So we take a look at our first example. We want to know what's the probability of drawing an ace and then a second ace from a deck of cards, assuming we replace the card. So the probability of A and B, so we first want to find the probability of A, drawing an ace. Well, there are 4 aces in our 52 card deck. Multiplied, when we replace that card we drew, there are still 4 aces and there are still 52 cards. We haven't changed because we replaced it. So I multiply fractions, we multiply straight across, so 4 times 4 gives us 16. And 52 times 52 is 2,704. And we can simplify the fraction 16 over 2,704 and becomes 1 over 169. So the probability that you draw an ace and then a second ace, assuming you replace the card, is 1 out of 169. So it's a very low probability. Our second example says if 78% of all students love math, what is the probability that 3 randomly selected students all love math? So this time we have 3 events. So we have the probability of A and B and C. It doesn't change how we perform it. We multiply all 3 probabilities. So the probability the first student loves math is 0.78 because that's 78% as a decimal. The probability doesn't change for our second student. It's still 0.78. And our third student, the probability is still 0.78 that they'll all love math. So when I multiply 0.78 times 0.78 times 0.78, we end up with 0.474552. So if you think in terms of percentages, that's a 47.4552% chance that 3 students chosen at random all love math. Now, probability can change in some situations if another event has occurred. So the most famous problem is drawing cards without replacement. So if I draw a card and I want to know the probability of drawing a king and then another king without replacing the card, it changes the second probability because I now have 1 fewer possible king and I have fewer cards left in the deck. So conditional probability is the probability that event A occurs given that event B has occurred. So the way we use to denote that is by a bar between it. So the probability of A given B, so that bar that we have right here represents given. It represents our conditional probability. So let's use a table relating career choice and job satisfaction to calculate probabilities. First, let's go ahead and find our totals before we look at our events. So the number of people in education that are satisfied, not satisfied, or undecided about their job is 200. The number of people in manufacturing, the total of satisfied, not satisfied, and undecided people is 360. And then the total number of people in sales that are satisfied, not satisfied, and undecided is 520. And we total that all together, we get 1,080. Next, we're looking at the total of satisfied, not satisfied, and undecided people. So total of satisfied is 450, not satisfied is 450, and undecided is 180. So when we look at what we've defined for our events, we have that event A is a person not satisfied in their job, and event B is a person in sales. So the first thing we want to find is the probability of A. So the probability a person is not satisfied in their job. So when we go to our column for not satisfied, we have a total number of people, 450, and then we compare that to the total number of people that have been surveyed. So the probability of A is going to equal 450 over 1,080. And we take 450 over 1,080 and we simplify it, we get 5 over 12. The next thing we want to take a look at is the probability of A happening given B has already occurred. So find the probability a person is not satisfied in their job given that person is in sales. So what we want to do here is we want to pay attention to the column, the row comparing sales. So we have 520 people total in sales, and the number of people who are not satisfied in their job is 300. So the probability of a person not being satisfied in their job given they're in sales, so the probability of A given B is going to be 300 out of 520. And when we simplify 300 over 520, we end up with 15 over 26. Our last example is to find the probability of B given A. So it's a little bit different than what we just did. So this time we're finding the probability that a person is in sales given that their person is not satisfied in their job. So again, we're going to go back to the column where people are not satisfied, which is a total of 450 people again. But this time we're looking at the number of people in sales, which is where the 300 is. So when you write the probability of someone being in sales given that they're not satisfied in their job, so the probability of B given A is going to be 300 out of 450. And when we simplify that fraction, we end up with 2/3. Now let's talk about what if we don't have a table. So there is a formula to find conditional probability, and it says that the probability of B occurring given that A has already occurred is the probability of A and B divided by the probability of A. So in our first example, we have that according to the U.S. Census, 19.1% of U.S. households are in the Northeast. In addition, 4.4% of U.S. households earn more than $75,000 and are located in the Northeast. Determine the probability that a randomly selected U.S. household earns more than $75,000 given it is from the Northeast. So let's first define our events. So event B is going to be a household that earns more than $75,000. And event A is going to be that the household is in the Northeast. So the probability of B occurring, given that A has already occurred, is going to be found by doing the probability of A and B divided by the probability of A. So in this case, we have the probability of A and B being 4.4%, which as a decimal is 0.044, and the probability of a household being in the Northeast only is 19.1%, which is 0.191 as a decimal. So when I divide 0.044 by 0.191, we end up with 0.2304. which as a percent is 23.04%. So the probability that a household earns more than $75,000 given it's from the Northeast is 23.04%. So using this formula and a bit of algebra, we can come up with a general multiplication rule for all events independent and dependent. So our multiplication rule says that the probability that events A and B both occur is the probability of A times the probability of B given A. So where the probability of B given A is the conditional probability that event B occurs given that event A has already occurred. So now we're going to look at some examples and we're going to determine which rule we're going to have to use to find the probability. So in our first example, we have that a card is drawn from a deck and replaced, then a second card is drawn, and we want to find the probability of getting a queen and then an ace. So because we are replacing the card, this is an example of an independent probability. So the way I find the probability of A and B, so the probability of getting a queen and then an ace, is found by taking the probability of A and multiplying it by the probability of B. So the probability that we get a queen, there are 4 queens in the deck of 52 cards, so that's 4 out of 52, times an ace. There are also 4 aces, and because we've replaced the card, there are still 52 cards in the deck. So when I do 4 out of 52 times 4 out of 52, we end up with 16 over 2704, which simplifies to 1 over 169. Next we have that if the probability of A is 0.32 and the probability of A and B is 0.16 and A and B are independent, what is the probability of B? So we're going to use the same formula, but we're going to plug in what we know. So we know the probability of A and B is 0.16. We have 0.16 equals the probability of A, which is 0.32, times the probability of B, which we don't know. So in order to solve for the probability of B, we divide both sides by 0.32. So the probability of B equals 0.5. Because when I do 0.16 divided by 0.32, we end up with 0.5. Next we have that if the probability A is 0.1 and the probability of B is 0.8 and the probability of A and B is 0.9, are A and B independent? So similar to the previous two, we're going to use our equation. So we know the probability of A and B is 0.9. If these two events are independent, that means that 0.9 has to equal probability of A, 0.1, times the probability of B, 0.8. So when I check that, 0.1 times 0.8 is actually 0.08, and 0.9 does not equal 0.08, so these events are not independent. Now we're going to take a look at a few examples where the events are dependent. So 3 cards are drawn from a deck and not replaced. We're going to use our multiplication rule to find the probability of getting 3 jacks, getting an ace, a king, and a queen in that order, and then getting 3 clubs. So we can extend our multiplication rule to 3 events. It works the same way as if it were 2 events. So first I have to find the probability of my first event. So we're trying to find the probability of getting 3 jacks. So I first want to find the probability of drawing 1 jack. Well, there are 4 jacks in a deck of cards, so that's 4 out of 52. And because I'm not replacing the card for my next draw, we're assuming the first card was a jack, which means there's only 3 jacks remaining, and there's 1 less card in the deck, which means there's only 51. So the probability the second card is a jack is 3 out of 51. And then we move to the third card. There's now only 2 jacks remaining out of a total of 50 cards. So the probability of 3 jacks is 4 out of 52 times 3 out of 51 times 4 out of 50, which equals 64 over 132,600, which simplifies to 1 out of 5,525. Which, as you can see, is a very, very small probability. And this is not 64. This is 24. 4 times 3 times 2 is 24. So it's 24 out of 132,600, which simplifies to 1 out of 5,525. So very, very small chance that if you draw 3 cards in a row, they will all be jacks. Next, we want to find the probability of getting an ace, a king, and a queen in order. The probability of an ace, a king, and a queen. So the probability of drawing an ace, there are 4 aces in a deck of cards, so that's 4 out of 52. And then when I draw a king, there are 4 kings in my deck of cards, but I've already drawn an ace, which means there are 51 cards left. And then for my third card to be a queen, there are 4 queens, but now I only have 50 cards to choose from. So that's 4 out of 52 times 4 out of 51 times 4 out of 50, which gives us 64 over 132,600. And when we simplify this fraction, we get 8 out of 16,575. So it's still a very, very small probability that you draw an ace, a king, and a queen in order from a deck of cards. So our last example is getting 3 clubs. So the probability that we draw 3 clubs. So first we want to find the probability the first card is a club. There are 13 clubs in a deck of cards. So the first probability is 13 out of 52. Then the probability that my second card is a club. There are now only 12 clubs remaining out of 51 total cards. And then the probability that the third card is a club is 11 out of 50. So we multiply our 3 fractions together. We get 1,716 over 132,600, which simplifies to 11 over 850, which is the biggest probability out of the 3 we just did. So you have a greater probability of drawing 3 clubs in a row because there are more clubs in a deck of cards. So 11 out of 150 chance that you draw 3 clubs in a row. So next we have the example that if the Michigan Wolverine football team wins 20% of their games, what is the probability that they will win 5 games in a row? And then we want to find the probability that they would lose 5 in a row. So when it comes to winning or losing football games, those are independent events. Just because you win one game doesn't mean you are going to win the next game or necessarily that you're going to lose the next game. So when we find the probability that they win 5 in a row, if they win 20% of the game, their probability stays the same. So that's 0.20 times 0.20 times 0.20 times 0.20 times 0.20. Because 20% as a decimal is 0.2. So I multiply 0.2 times itself 5 times, we get 0.00032, which is a percent of 0.032. When we look at the probability that they will lose 5 games, so the probability that they lose 5 games, if they win 20% of the games, that means they have to lose 80%. So that's going to be 0.8 times 0.8 times 0.8 times 0.8 times 0.8. So I multiply 0.8 by itself 5 times, we get 0.32768, which is a 32.768% chance that they will lose 5 games in a row. So last, we're going to take a look at a table example. So most students here at DACC have Delaware or Buckeye Valley as their home school. If the probability of being from Delaware is 60% and the probability that a student is female, given they are from Buckeye Valley, is 20%, we want to complete our table. So the first thing we're going to use is the fact that the probability that a student is from Delaware is 60%. So because we have a total of 500 students, we know that 60% of our 500 has to equal the number of students from Delaware. So when I do 0.60 times 500, we get 300. So it tells me the total number of Delaware students is 300, which also helps me figure out how many students have to be from Buckeye Valley, since my total is 500. So that tells me that 200 students have to be from Buckeye Valley. Next, we use our probability that a student is female given they are from Buckeye Valley. So the probability that a student is female given they are from Buckeye Valley is 20%. So when we go in our table, we have a students from Buckeye Valley and we know that the probability they're female. So that is going to be this box in our table. That is 20%, and that is 20% of our Buckeye Valley students. So we know that 0.20 of 200 gives us 40. So we know that we have to have 40 female students from Buckeye Valley. And this actually gives us enough information to finish filling out our table. So if I do 250 minus 40, we get that we have to have 210 female students from Delaware. And then when we go across, now that we know our number of female students from Delaware, that tells us our number of male students has to be 90, and that our number of male students from Buckeye Valley has to be 160. And when I double check, 90 plus 160 is still 250, and 160 plus 40 is 200. So all of my rows and columns sum to the correct number. Let me know if when you're working on the Section 2 assignment if you have any questions. I know probability isn't always the easiest concept for some people, so please feel free to ask any questions.